So let's look again at how the current and the voltage gets affected when we hook up a parallel circuit. Firstly, we'll look at the current. And we'll use the water pipes model again to picture the current. So in parallel, the water flows through the pipes and all the water gets carried through this bit. But when we reach the intersection or the junction between the two parallel sections, the water needs to split up and go two different ways. So only half the current is going to flow each way. So through the parallel sections, which are these yellow bits here, that part and that part, only half the current will flow, so the water's moving much slower. And then when it joins up again, then the current is back to full speed again. So in the first part it was full as well. So overall, the current changes in parallel. We can say the current splits equally in each of the parallel parts. Or each parallel path. And let's draw a circuit diagram to actually demonstrate that. So we'll have our power source, and we'll have a lamp. That's our first section. And now we'll have another lamp, and we'll connect that in parallel. So if we put an ammeter in the first part here, this is measuring the full current. So that full current might be 10 amps. But then if we put ammeters down in the parallel sections, the current has been split in half, because half the electrons travel one way and half travel the other way. So the ammeter will only measure 5 amps on this one and 5 amps on that one. But back up here, where the current has joined together again, this ammeter is going to measure 10 amps again, as all the electrons come back together. What happens with the voltage though? So let's use the trucks model again to picture the voltage. So we can see here, just like always, at the negative end of the battery, electrons are being produced and they're being given lots of energy, which is the voltage. So they travel down through this part of the circuit, but then half of them will continue through that loop and the other half of them will go down to the other parallel section. So if we follow the green electrons, all the green electrons will flow through this lamp and then they'll join back to the main circuit here, which means they only have one object to give their energy to. So they're going to dump all of their energy to this one light bulb. And then the red electrons, they're flowing down this part of the circuit and they only pass through one light bulb as well. And then they come back up and they join back to the main part of the circuit. So these electrons, they only dump their energy in one light bulb too. So actually, in a parallel circuit, each load or each resistor is receiving the full amount of energy from each electron. So in other words, the voltage is the same as it would be if we just had one light bulb. So voltage stays the same in parallel. And that's because parallel parts receive the same amount of energy. And the reason for that is like we saw here with the following each electron, because each electron only drops off its energy at one particular load. Each electron drops energy, or gives it, at one place only. Whereas if we look back at the series circuit, each electron had to deliver its energy to two of the lamps, so it had to halve its energy. So if we want more than one light bulb to be connected, which often in a room you might want two lights to come on with the one switch, then we need to connect them in parallel so they don't lose half their energy and become dimmer. So in parallel circuits, the current gets reduced, but the voltage stays the same.